Hello everyone. Once again, welcome to this KTHM e-learning channel. In this lecture, we are going to derive expression for Laplacian operator in various coordinate system. In general curvilinear coordinate system, in Cartesian coordinate system, in cylindrical coordinate system, and in spherical polar coordinate system. Let us start. In previous lectures, we have learned three operators: gradient, divergence, and curl. As well as we have derived expression for gradient, divergence, and curl in various coordinate system. In this lecture, we are going to discuss Laplacian operator. Laplacian operator. Then what is Laplacian operator? Laplacian is a differential operator given by divergence of the gradient function. This operation, divergence of the gradient function. Del phi is a gradient function, and divergence of gradient function is the Laplacian of the scalar, and it is denoted, this Laplacian operator is denoted by del square. The significance of Laplacian: Laplacian gives the flux of density of the gradient flow. Flux of density of vector is divergence, and gradient is a vector. Therefore, flux of density of the gradient flow is Laplacian. Get this point clear with two fundamental equations of electrostatics. Two fundamental equations of electrostatic, namely the Poisson's equation and Laplace's equation. If charge distribution at certain point, if charge distribution at certain point is given by rho, that is charge density, then the divergence of electric field is, then divergence of electric field del dot E bar is equal to rho upon epsilon 0. As well as the expression for electric field in terms of scalar potential phi, which we have already discussed, that E bar is equal to minus del phi. That this del phi is a gradient, and negative gradient of this potential is the electric field. The electric field is E bar, where phi is a electric potential. Then the Laplacian, del dot del phi is equal to del square phi. Using these two expression, from these two expression we get del dot del phi is equal to del square phi is equal to minus rho upon epsilon 0 is the Poisson's equations. And if region of space has no sources of charge, that if the region is charge free region, then rho is equal to 0. Then del square phi is equal to 0. If substitute rho is equal to 0, then we get del square phi is equal to 0, and this is the Laplace's equation. The solution of this equation, the solution of Poisson's equation, gives the electric potential phi at a point caused by given charge distribution. This is one of the application of the Laplacian operator. That is, the solution of Poisson's equation gives the electric potential at a point caused by given charge distribution. Let us derive Laplacian operator in general curvilinear coordinate system. The expression for gradient in general curvilinear coordinates, this we have already derived in previous lectures, that del psi is equal to E1 cap upon H1 dava psi by dava U1 plus E2 cap upon H2 dava psi by dava U2 plus E3 cap upon H3 dava psi by dava U3. And del psi is a vector function. Therefore, this may be written in vector form, that F bar is equal to F1 E1 cap plus F2 E2 cap plus F3 E3 cap, where F1, F2, F3 are components of F bar along U1 curve, U2 curve, and U3 curve. Comparing these two equations of gradient psi, we get F1 is equal to, from the first term, F1 is equal to 1 upon H1 dava psi by dava U1, F2 is equal to 1 upon H2 dava psi by dava U2, and F3 is equal to 1 upon H3 dabba psi by dabba U3. Now this del square psi is equal to Laplacian operator operating on scalar function del psi is equal to divergence of this gradient del dot del psi, but del psi is f bar, therefore del bar dot f bar, divergence of vector. But we have already derived the expression for divergence in general curvilinear coordinate system that we have to use here. The divergence of f bar del dot f bar is equal to 1 upon h1 h2 h3 dabba by dabba u1 of f1 h2 h3 plus dabba by dabba u2 of f2 h1 h3 plus dabba by dabba u3 of f3 h1 h2. Substitute f1 is equal to this here, f1 is equal to this, f2 is equal to 1 upon h2 dabba psi by dabba u2, and f3 is equal to 1 upon h3 dabba psi by dabba u3. Then we get del dot del bar psi is equal to 1 upon h1 h2 h3 dabba by dabba u1 of 1 upon h1 dabba psi by dabba u1 h2 h3 plus dabba by dabba u2 of 1 upon h2 dabba psi by dabba u2 h1 h3 plus dabba by dabba u3 1 upon h3 dabba psi by dabba u3 h1 h2. This may be written in another way: 1 upon h1 h2 h3 is dabba by dabba u1 of h2 h3 upon h1 is h2 h3 upon h1 dabba psi by dabba u1 plus dabba by dabba u2 h1 h3 upon h2 dabba psi by dabba u2 plus dabba by dabba u3 h1 h2 upon h3 dabba psi by dabba u3. This is the Laplacian of scalar in general curvilinear coordinate system. If we eliminate psi from this expression, then we get the expression for Laplacian operator. This is the expression for Laplacian operator in general curvilinear coordinate system. In next part of this lecture, we are going to use this expression to derive Laplacian operator in Cartesian coordinate system, in cylindrical coordinate system, and in spherical polar coordinate system. First, let us derive Laplacian in Cartesian coordinate system. In Cartesian coordinate system, the coordinates are x, y, z. Therefore, u1 is equal to x, u2 is equal to y, u3 is equal to z. And the three scale factors h1 is equal to 1, h2 is equal to 1, h3 is equal to 1. Substitute u1 is equal to x, u2 is equal to y, u3 is equal to z, and h1 h2 to h3 equal to 1. Then we get del square psi is equal to dabba by dabba x of dabba psi by dabba x plus dabba by dabba y of dabba psi by dabba x plus dabba by dabba z of dabba psi by dabba z. Or this del square psi is equal to dabba square psi by dabba x square plus dabba square psi by dabba y square plus dabba square psi by dabba z square. If we eliminate psi, remove psi from this expression, then we get Laplacian operator in Cartesian coordinate system. That del square is equal to dabba square by dabba x square plus dabba square by dabba y square plus dabba square by dabba z square. Now derive Laplacian in cylindrical coordinate system. The cylindrical coordinates are rho, phi, z. Therefore, u1 is equal to rho, u2 is equal to phi, u3 is equal to z. And three scale factors h1 is equal to 1, h2 is equal to rho, h3 is equal to 1. Substitute these values in this expression of Laplacian in general curvilinear coordinates. That h1 1, h2 rho, h3 1. Therefore, this 1 upon rho. u1 is rho, h1 h2 is rho, h1 h3 h2 is rho, h3 h1 1, and this u1 is rho. Therefore, rho dabba psi by dabba rho plus u2 pi, h2 rho, h1 h3 1, and u2 is pi. Here z z, and this h2 is rho, h1 h3 1. Therefore, if we simplify this expression, derive this product term rho dava psi by dava rho with respect to rho and multiply throughout by rho. Multiply throughout by rho. Sorry, divide throughout by rho. This rho is constant with respect to phi, therefore take it outside the partial derivative. This rho is constant with respect to z, therefore take it outside the derivative. Then this row get cancelled with this row and this row, we get 1 upon rho square. In this way, we simplify this, then del square psi is equal to dava square psi by dava rho square plus 1 upon rho dava psi by dava rho plus 1 upon rho square dava square psi by dava phi square plus dava square psi by dava z square. And the Laplacian operator del square is equal to dava square by dava rho square plus 1 upon rho dava by dava rho plus 1 upon rho square dava square by dava phi square plus dava square by dava z square. Let us derive Laplacian in spherical polar coordinate system. The spherical polar coordinates are theta, phi. Therefore, u1 is equal to r, u2 is equal to theta, u3 is equal to phi. And the three scale factors h1 is equal to 1, h2 is equal to r, and h3 is equal to r sine theta. Therefore, in this expression, wherever h1 substitute 1, replace h2 by r, replace h3 by r sine theta, replace u1 by r, u2 by theta, and u3 by phi. Then we get del square psi is equal to 1 upon r square sine theta, dava by dava r of r square sine theta dava psi by dava r, plus 1 dava by dava theta of sine theta dava psi by dava theta, plus dava by dava phi of 1 upon sine theta dava psi by dava phi. Then this 1 upon r square dava by dava r of r square dava psi by dava r, because this sine theta is constant with respect to r. Take this sine theta outside the partial derivative, it get cancelled with this term, therefore we get this first term. Then the second term 1 upon r square sine theta dava by dava theta, this r square sine theta, and this dava by dava theta of sine theta dava psi by dava theta plus 1 upon r square sine theta, 1 upon r square sine theta dava square psi by dava phi square. This 1 upon sine theta, because sine theta is constant with respect to phi, therefore this 1 upon sine theta and this r square sine theta. Here we get r square sine square theta, or the Laplacian operator in spherical or polar. If we eliminate psi from this expression, then we get, this is the expression for Laplacian operator in spherical polar coordinate system. That's all in this lecture. Thank you.